In this video I want to talk about series and parallel combinations of capacitors and inductors. So similar to what we had with the resistors, we can have series or parallel combinations of inductors and capacitors, and we can reduce all of them into a single inductor or capacitor. The way we do it is very similar to what we did with the resistors, by applying Kirchhoff's voltage law or KVL and also Kirchhoff's current law or KCL. If you remember before, we said that resistors that are connected in series carry the same current. This is in fact true for all types of components that are connected in series. Also, if you remember, we said that resistors that are in parallel have the same voltage. Again, this is true for all types of components that are connected in parallel. So let's just see how these laws can be applied to interconnection of inductors and capacitors. So I start with a series combination of inductors. So as you can see here, we have three inductors that are connected in series. So since they are all connected in series and there is no other element connected in these nodes, they all carry the same current. So I name the current as I, but each one of them have their own individual voltages. So using the equation that we had for the voltage of an inductor with respect to the derivative of its current with respect to time, which was V was equals L di over dt. Now for each one of these inductors, we can find their individual voltages. So for the first inductor, V1 is going to be L1 multiplied by di over dt. For the second inductor, it's going to be V2 equals L2 multiplied by di over dt. And finally, for the third inductor, it's going to be V3 equals L3 multiplied by di over dt. But now let's say we want to find the equivalent inductor that is connected between this terminal and this terminal. So basically, if we have these three inside the black box, what is the terminal behavior of this black box? So as you can see, the three voltages V1, V2 and V3 are summed together to create the voltage between the first terminal and the last terminal here. So V equals V1 plus V2 plus V3. We know that each one of these individual voltages have their own equations, but this part is common between the two. The derivative of I with respect to t is common, so we can factor that out, and what we are left with is this summation L1 plus L2 plus L3 multiplied by di over dt. So therefore, the equivalent inductance of n inductors that are connected in series is actually the sum of all those inductances. So Leq is going to be L1 plus L2 plus L3 all the way to Ln. So as you can see, this is very similar to the connection of resistors in series. So this is how you can help yourself in memorizing this equation, that inductors in series are similar to resistors in series in terms of finding the equivalent inductance. But there is one difference, because with resistors we didn't have any initial voltages or initial currents, right? But with inductors we have what we call as the initial current. So if the original inductors carry an initial current of IT0, and remember, this current needs to be the same for all of them to be able to connect these three together. Otherwise, we may have sudden changes in the current, which we know that it is not possible because of the equation that we had for the voltage of the inductor. So these three initial currents must be the same. So if the original inductors carry an initial current of I at T0, the equivalent inductor carries the same initial current. So as you can see, we have L1, L2 and L3 all connected in series, all having this initial current, and this configuration is simplified to one single inductor with the value being the equivalent inductance LEQ, which is equal to the sum of L1, L2 and L3 with the initial current of I at T0. Now let's just see what happens if we have inductors that are in parallel. So here we have L1 with the current I1 being in parallel with L2 with the current I2 being in parallel with L3 with the current I3. And this time each one of these inductors have their own different initial current. What we want to do is that we want to see if we put this all inside the black box, what is the terminal behavior of this black box. So more specifically, what is the relationship between the voltage between these two terminals and the current that enters the black box. To get the equation, what we can do is that we can write the KCL for this node, because we know that the sum of all the currents that enter any node equals the sum of all the current that leave that node. So here if we have I entering this node and we have I1, I2 and I3 leaving the node, I should be equal to I1 plus I2 plus I3. So that means that we need to write the equation for the current of these individual inductors first. We know the general equation. So the general equation was I equal 1 over L, the integral from T0 to T, V d tau plus I at time 0. So this was the general equation. For these individual inductors, one thing that we know is that since they are all connected in parallel, their voltage is the same. So that means that I1 is going to be 1 over L1, the integral of voltage between these two terminals, over time plus the initial current. I2 is 1 over L2, the integral of the same voltage over time, plus I2 at the initial time. And finally I3 is 1 over L3, the integral of the voltage, the same voltage, as you can see here, plus I3 at time T0. So now if we write the KCL equation for this node, we see that I, or the current that enters this combination, should be equal to I1 plus I2 plus I3. So in these three equations, what is common is this part, the integral of the voltage. So we can factor that out. So if we factor that out, to the left we have 1 over L1 plus 1 over L2 plus 1 over L3 multiplied by this integral plus I1 at time T0, I2 at time T0 and I3 at time T0. So if you put this equation next to the general equation, you see that this part is now represented by this summation. So that means that the equivalent inductance for this circuit can be calculated by the following equation. 1 over the equivalent inductance equals 1 over L1 plus 1 over L2 all the way to 1 over L1. Again, this is a similar situation that we had with the resistors. So if we had a bunch of resistors that were connected in parallel, 1 over the equivalent resistance was the summation of 1 over the individual resistors. So 1 over R1 plus 1 over R2 plus all the way to 1 over Rn. But now, since this is an inductor and inductors can store energy in the form of initial currents, we have this additional equation for the initial current of this combination, which is going to be the summation of all the individual currents. And these equations are directly derived from applying the KCL on the top node of this circuit. So far we have seen the result of having inductors in series and also having the inductors in parallel. What about capacitors? For capacitors, we basically need to do the same analogy. So let's just go over the capacitors that are connected in series first. So when they are connected all in series, we know that the current that goes through them is the same. So if you remember, we said that I equals C dV over dt, which basically would translate to V being equal 1 over C, the integral of the current d tau plus the voltage at time t0. So now to get the voltage for this series combination that we have here, we need to sum all the individual voltages. So this one, remember, it was from t0 to t. So for each one of these capacitors, we can calculate their individual voltages, and that individual voltage has this integral in common because the current that goes through these capacitors that are connected in series is the same for all of them. So when we write down that equation for the combination and we put it next to the general equation that we have, we see that the equivalent capacitance is going to be 1 over C EQ equals 1 over C1 plus 1 over C2 all the way to 1 plus 1 over Cn. As for the initial voltages, they are going to be summed together. And this is something that is understandable because if you write down the loop equation or the KVL equation here, you see that negative V plus positive V1 plus positive P2 plus positive Vn equals 0. So that means that for the initial voltage, they are going to all be summed together. Of course, if the direction is reversed for some of them, that means that that specific one should have a different sign than the other one, right? But this is something that you will see later on with more examples. So as you can see, capacitors act similar to conductance. So inductors act similar to resistors, capacitors act similar to conductance. So this is what you can use to remember how the series and parallel combinations of inductors and capacitors are being calculated. And finally, when we have capacitors in parallel, if you want to write down the equation for this combination, we know that I for each one of these capacitor equals C dV over dt. So since the voltage across all of these capacitors is the same because all of them are connected in parallel, what we only need to do is that we need to factor out the derivative of voltage with respect to time. And then we write the KCL for this node, which basically means that I, the current that enters the node, equals to the sum of all the currents that leave the node. So using this analogy, we can see that the equivalent capacitance is going to be the sum of all the capacitors. You might ask, what happens to the initial voltage? So first of all, if you want to connect a bunch of capacitors in parallel, you need to make sure that their initial voltage is the same. Otherwise, because of the equation that we had, that may translate to having infinite current, which is not physically possible. But if all of them are having the same initial voltage, that initial voltage is basically present for the equivalent circuit as well. So in this video, you learn how having capacitors and inductors in parallel and series can be used to derive the equivalent circuits. We saw that inductors behave similarly to the resistors, and we saw that capacitors behave similarly to the conductors. Of course, you need to take into account that inductors have initial current, and that initial current in some of the cases becomes important. This was something that we didn't have with the resistors. Similarly, for the capacitors, we have the initial voltage, which was not present for the conductance.